Hello everyone, and welcome again to this class. And let us quickly move to what we were doing. And we were doing some example which we have to find whether that transformation was canonical or not, depending upon what type of uh, method we are going to use. So quickly let me move to that place, and that is I think is okay. We were doing this example, and in which we have been given this transformation, and we had already find using this perfect differential method that this transformation is going to be the canonical, because we have already find that this is going to be my perfect differential, this transformation. And then based on that transformation, this if you have integrated, if you remember, so I have this f is this thing. Then we had find that what are the generator, what possible generator could be. So if this is, if you want this is f1, if you want this is f2, if you want this is f3, you can find depending upon whether what variables your f3, f2 and f1 depends. That if you remember, that we have figured out what is the f3 and what is f2, and the same way you can figure out what is going to be the f1 generator for this corresponding canonical variable. Okay, so what you have to be precise, that whatever this f is coming out, that if you want to prove that this is going to be f3 generator, then you have to look for that your expression has to be on those variable depending on which your f3 is depending, a small p, a small q, and then that is the important part. Okay, now let us try to look for this particular problem from the second method, that if this transformation is going to be canonical. So then if you remember that we established that these are the four differential, partial differential. If any one of these depending upon what kind of transformation is given, that if any one of these fulfills, then that transformation is going to be the canonical transformation. Okay, so in our case, the first thing is very simple, that this q is given in terms of the small q. So what I have, you can look for this first differential, and so you can calculate it, because you have already calculated with respect to q. So we're differentiating with respect to q, that is del q of log 1 by q sine p, and then del q of sine p by q. So this is going to be simply q upon sine p, because log is going to be 1 upon that 1 upon q sine p, that is going to be q upon sine p. And this is going to be, because you were differentiating with respect to q, this is going to be minus 1 upon q square, so minus 1 upon q square sine p. So this term is minus 1 by q, this term. So now I have to figure out what is this term. So if this also comes out to be minus 1 by cube, then the transformation is going to be the canonical transformation. So for this I need a relation that that I have to integrate the small p with respect to capital P, and that can be done in terms of here, because the relation which gives you a small p in terms of p. So so I have p equal to cot p, and then I have already, because you need to know that this is going to be this is in terms of, because you see that this is the base is small qp. So here everything was in terms of the small q and the small p. Okay, now your base is basically qp. So capital Q and P. So then in the expression you must have either, because you are doing with respect to qp, so then the expression must represent in terms of the q. So unless you can do this, this expression is this expression itself give you that p is this cot inverse this p by q. Okay, so that is and that is what is here. Okay, so now you can have this delta p upon delta p, you can find it out. Okay, now what have been done is q we have already calculated, this is e to the power minus q sine p, from taking this this we have already done in the previous class. that if you take the log of a exponential on the both side, you get this thing. Okay, so you put q equal to e to the power minus q sine p, and then you have cot p. So life becomes simple. That becomes e to the power minus q cos p. You don't have to do this cot inverse p by q differential. So now I have the simple expression in terms of a small p and capital P, so that the differential will be easy. So now this small p is cos inverse p e to the power cube. So now if we do p upon p, this is what integral we have to find out. So then what you're going to get is this is cos inverse, this is going to be 1 upon 1 minus x squared. So if you have cos inverse x is, so this is going to be 1 upon under root 1 minus x squared. So then you have x is p2 square, and then with respect to whatever it is with respect to p, so this with respect to p is going to be 1. So this is going to be minus, because p is going to have this thing, and then you're going to have e to the power q here. Okay, now what you're going to have is because this p e to the power cube, so the p e to the power cube is going to be cos p, because you have the relation p equal to e to the power q cos p. So you have p equal to e to the power minus q cos p. So if you multiplied by e to the power cube and e to the power cube, so this will become 1, and then you have e to the power cube cos p is cos p. So p e to the power cube is cos square p, and then 1 minus cos square p is under root is sin p e to the power minus q upon sin p. And then you have this relation that e to the power minus q upon sin p is going to be 1 by cube. Okay, so this is going to be 1 by cube. So this 1 by cube is equal to delta q by delta. So this first integral is satisfied in this case. In this transformation, this first integral is satisfied. So that's why in using the second method you have the transformation showing that this is going to be the canonical transformation. Okay, now let's move to the third transformation, third method, that is going to be based on the Poisson bracket. So I have the same transformation with me, q equal to log 1 by q sine p, p equal to cot qp. So naturally, because we are going to have this qq is 0, there is no need pp is 0. So just we need to find the qp, that is going to be 1. If this is 1, then this transformation is going to be the canonical transformation. Now how we define this Poisson bracket? Qp is capital Q with respect to p and p and p and q. This is how. So I need to find this this relation, this and this, and then try to find out what ultimately comes off. If this is equal to 1, then the transformation is going to be the canonical transformation. So first thing we are going to find delta q upon delta q, that is we have already find it out, that is minus 1 by cube. This already find it out, minus 1 by cube. Okay, and then delta p upon, and then delta p upon capital P, delta p upon p. This is delta p upon p. So p is q cot p. So with respect to p, so q will remain same, and with respect to p, this is cot p is going to be minus cosec square p. So this is what I have. The first two term we have, and then I have delta q upon delta p, delta q upon delta p. Okay, so delta q upon delta p, you already figure it out here, delta q upon delta p. Okay, this one is, so so there is no need to calculate it, because when you're differentiating this with respect to p, the delta p of this whole thing and delta p of this whole thing. So this is going to be 1 upon this whole thing. This is going to be q upon sine p, and with respect to p you're doing, so this sine p is going to be the cos p. So this is going to be q cancel out, and then cos by sine is going to be the cot p. So this is going to be the cot p. So this is there, and then what you have, delta p upon delta q. So what is going to be delta p upon delta q? This p is q cot p. So if I find delta p upon delta q is going to be cot p. Okay, so everything I have cot p. Now I'm going to put this all the four partial differential. This one is minus 1 by cube. So this one is minus 1 by cube, and this one is delta p upon p is minus q cos square p minus q cos square p, and then I have minus here, and then delta q upon delta p. Delta q upon delta p is cot p, so cot p, and delta p upon delta q is again cot p, so this is going to be the cot p. So this is minus minus plus, this q will cancel out, okay. So this is going to be cosec square p, and then I have negative here, and then cot square is going to be cot square, that cot p is going to be cot square p, and you know that this is cot square p is 1 plus cos square p. So with this relation, this is going to be 1. So now I figured out this Poisson bracket between this q and p, the transformation which is given, this q and p, in terms of this q and p. So if I calculate the Poisson bracket of these q and p, and this comes out to be 1, and which is exactly is coming out to be 1, then this this transformation from this method, Poisson bracket method, is also going to be the canonical transformation. So you have three different approaches to show that particular transformation is going to be the canonical transformations. Whatever suits you, depending upon what kind of transformation is given, is going to be easy for you. So first you try to find out the perfect differential, this one, and then based on that perfect differential, that you can calculate what kind of generator you find, and then finding that generator, you had to keep in mind that the generator, your expression of generator should be in terms of the variables on which the generator is depending, okay. So, and then the second method you can use, depending upon that what kind of differential along these four is going to satisfy any one of these, then that is canonical. And third one is that if you calculate the Poisson bracket, if this is given in terms of small q as small p, then you have to find out this Poisson bracket of a small q as p, and if this comes out to be 1, then the transformation is canonical, simple as one. Okay, and then for generating function, you have to find this differential, perfect differential, so that will be easy for you to find the generating function, okay. Then I have the same let us try to quickly do this one with standard transformation, is that I have this q and p, and this we have to find out that whether this transformation is canonical, or then we have to find the generating function. So now first I'm going to find the perfect differential, that is p dq minus p dq is going to be my perfect differential, okay. This is my perfect differential. So then this I have to find dq. So if I find dq, q is there, so I have to, this is log of this, so this is 1 upon this, and then you have to differentiating with respect to q. So this is q here, so this is going to be 1 upon 2 under root q, okay, because when you're representing q, that is going to be del q of q 1 by 2, this is going to be 1 by 2 q half minus 1, and then del q of q, okay. So this is going to be half, and this is q to the power minus half, so that is going to be 1 upon 2 root cube. This you know that this is 1 upon 2 root cube, and cos p as such, because it's not depending upon q. Then you do with respect to p, then what you have, this 1 upon this is common, because this is log, and then q remains same, and cos p becomes minus of sin p, that's why with dp, okay, and with dq is here. And now you multiplied with this p is twice, so I multiplied by with this p. So if we do this whole 1 upon cos p is gone with this, and then you get the first term, if you concentrate the first term, 2 under root cube is cancel out, and you have sin p cos p dq, sin p cos p dq. And for the second term, this whole is, this is gone with that, and for the second term, with this q and this q becomes under root q, this q, and this 2 is there, and then sin p and sin p sin square dp, okay. So now then I have to subtract it from p dq, so I subtract it from p dq, so this is p dq, and the whole the whole this expression is here in front of you. Now I write this because sine 2p is 2 sine p cos p. So I can write this sine p cos p as 1 by 2 of sine 2p. So this is sine p cos p is written as 1 upon 2 sine 2p dp, and this 2q is there, sine square p 1 minus cos 2p upon 2. So if you do this, so from doing this we have this q dp, I have p dq is there, and this q dp with this 2 will cancel out, so I have the perfect differential in this, and the rest of the part is also going to give me the perfect differential. So in any ways this transformation is going to give me this perfect differential. You can see it is very direct. So this transformation is also going to be the canonical transformation. Now the rest is finding this. You have to find that this transformation, the generator of this transformation is f3. So because again you see that f is my df is dp, so I can, if you integrate it, so I get f equal to qp height. So then this goes this side, I get f minus p. So this is my f3 generator. This is already we have. So this is going to be half q sine 2p. But again my f3 depends upon a small p and capital Q. So I have a small p's here but no capital Q. No capital Q. Instead I have a small q. So then I have to use this transform this small q into capital Q. Okay. So now I have this relation, that is q equal to log. So if you take the exponential both side, so e to the power q is 1 plus q cos p, and then from here I can find out this q is going to be e to the power minus 1 and then divided by cos p. And then if you take a square of both sides, this is q of this. So now what I have is q in terms of capital Q. So what is I need is q in terms of the capital Q. So I can put it here in f3. My f3 is minus q sine p cos p, because this is sine 2p I have written as 2 sine p cos p. The 2t will cancel out, minus qp sine p. So in place of q I write this e to the minus q, and then I have sine p. So small p dependent is there and capital P dependence there, no extra dependence is there. So finally what you get is my sine p and cos p is there. So this cos p square will get 1 cos from here, and sine and cos will come tan p. So this is how you see that my f3. If you want to figure out my f2, what is my f2, if you want to figure out what is my f1, then you have to transform this this whole expression depending upon the given transformation equation, that on which your f2, like f2 depends upon this q capital P and T. So then this has to be in q capital P and T. Okay, and your f1 depends upon this small q capital Q and T. So the expression must be in terms of a small q capital Q and T. Then you can find f1, f2 and f3. So this is how you get your transformation. The same thing you can find using the differential equation. You try using find the differential equation, using the you will find whether this transformation is canonical in terms of the Poisson bracket. You calculate this q and p Poisson bracket, and then if comes out to be q comes out to be 1, then this is going to be the canonical transformation, and naturally it is going to be 1, because already you have in front of you that this is a canonical transformation. So I have another example for this, that is so I'm not going to do all the examples, figure out it here in front of you, because it will take my time, unnecessary time. So I'll move to some other place, some other topic. So but I have solved all these here for your convenience. So first try to do yourself, try to calculate yourself using all the 3 methods, that you are able to figure out that whether the transformation is canonical or not. And if you're not able to figure it out, you can help it out from this these notes that these I have given to you, and from the basis of this, how to find this generating functions, and how to find the partial differential for this particular problem. You can find it this. Similarly, there is another example which is standard. Then again you apply the same procedure. Try to find yourself. Unless until you don't find, you're not going to learn the thing. So you have to calculate it yourself, whether that is the Lagrangian problem or the Hamiltonian problem, or you proof of that this particular transformation is going to be the canonical transformation. All these cases you have to do, you have to pen down from yourself, otherwise you're not going to learn the things to how to calculate it. So in the same way, I have calculated it here itself on these notes that will be provided to you, and but try to calculate it yourself first. So I have here also I've calculated f3 f1 generating function and show that, and this f3 also. There's another example I've given you. This is all some example from there. Now also from the second method, from the Poisson, this is q. This transformation in terms of this, you see in terms of the small variable in q. Earlier all the was q in terms of the qp, and this p and pqp. Now this particular example is in terms of this q is given in terms of the qp, okay, and p given in terms of the qp, okay. So the same situation is there. This is second method, qp sine q. This is already I have done. This is called qp sine q. From the perfect differential method I have already calculated it, okay, from perfect differential method. And then this is the second method using the Poisson bracket, okay. The same is there. This is again I have given you a lot of example for this, and solve it. The main thing is I have solved it for you, so that if you get stuck while calculating by yourself, then you can take help from this side, okay. And this is one which you have already calculated while doing in the harmonic oscillator, okay. So this is one which is this is another type of that the transformation equation is given to you like in terms of q and p, and some constant is alpha. So this, let me find that for what value of alpha and beta the transformation is going to be the canonical transformation, okay. So this is what you have to figure it out, that the transformation is going to be the canonical transformation. Now what you need to do is that you apply the perfect differential, that is my p dq minus p dq is going to be perfect differential df. So the same way I'm going to calculate this p dq. So dq here I have is, because this is q alpha, so that depends alpha q to the power alpha minus 1, and then it depends upon beta. The cos beta remains same, and then this cos beta p is basically the argument of that, and then I have dq. And then what you have with respect to, what you have to do with respect to p, so beta with q alpha will remain same, and then you have to differentiate this cos beta becomes minus of sine. So this is minus of sine beta, and then this is argument of this is of the sine, that is beta dp, and then I have multiplied by this p, capital P. This is q alpha sine beta p, q alpha sine beta p. So now you multiplied it, you get an expression. I'm not going to multiply it, and you figure it out, this p dq, and then I subtract it from this p dq, okay. So I subtract it from this p dq. So p dq and this whole is there. So what we need is we have to impose that, because we know that the transformation is going to be canonical, and for that condition we have to find what is the value of alpha and beta, for what value of that transformation is going to be canonical. So then we had to figure it out. So first we gathered that dq and dp coefficients, because this all together is going to give me d of qp, okay. So then if for this has to be this, if you see that this is going to be equal to this is p dq. Okay, so you have dqp is p dq plus q dp. Okay, so you have already p dq is there. Now I have p q dp, so dp is there, so this is going to be q. Okay, so what I want is half beta q to the power 2 alpha dp is going to be equal to q. Okay, so now what you want is to be perfect differential, that is this is half is there, beta q to the power alpha minus 1, and this is going to be q dp. So I write this q2 alpha as 2 alpha minus 1 and then multiplied by q, so this becomes q dp. Okay, so now what condition I have is this whole is has to be equal to 1. Okay, so I have already q dp, what I want is q dp, and I want this to be 1. So if this to be 1, okay, so condition is has to be on this q2 alpha minus 1, because you can put condition on beta equal to 2, then there is no. So if q alpha 2 alpha minus 1 is going to be 0, so then becomes is going to be 0, so then alpha becomes half, and then when alpha becomes half, what do you half beta q to alpha minus 1, this is half beta q to alpha minus 1. So this is, if this is going to be 1. So for this if this is going to be 1, so this is one condition, that beta, if you put beta equal to 2 and this 2 alpha minus 1 equal to 0, so this from there you get the condition of alpha equal to half and beta equal to 2. So for this condition, then this if you put this alpha equal to half and beta equal to 2 into this expression, for alpha equal to 2, beta equal to 2 alpha and equal to half in the whole calculation, so what you're going to get is p dq q dp. This we already have here, p dp, and then if you put half, this is 2 and this is half, so will cancel out, this is become q, and this 2 will cancel out, so you have q dp. So you have already this q dp, and then this third term. So if you concentrate here, you're going to put this is q 2 into half minus 1, and then half into 1 by 2, because this is half, and then you have sine 2, beta is 2, so into 2p dq minus q 2 into half, and then beta is 2 by 2, and then you have cos 2 beta p dp. So what do you have, this is 2 will cancel out, so 1 minus 1 is 0, this is q to the power 0, so you have 1 by 4 sine 4p dq. So you have 1 by 4 sine pq dq, and then this is q, and this will cancel out, q cos, and this beta is 2, to cos 4p dp. So this is going to be q cos 4p dp. Okay, now this is my perfect differential, and this is again my perfect differential, so thus this becomes a perfect differential. So now for the alpha equal to half and beta equal to 2, I'm going to have the perfect differential. Okay, and then you can find the generating function. So this sort of expression can also be, or problem can also be used, where you're imposing, considering that the transformation is canonical, you have to find out the certain constant variable for which value of that is going to be the canonical transformation. Okay, so from the second method also you will get your I have solved it here, and you can find it from this Poisson bracket method, that this should comes out to be 1. So then you can demand that this is going to be 1, and then this you can find alpha and beta variables. Okay, and then similarly you can find out this differential. So I think I have 6, 7, 8 example. I have worked it out, and then you can see the flavors of all sort of transformation equations, and how to do it, how to find the generating functions. So I think this is all for today's lecture, and then I will stop here, and we'll meet soon in the next class, where we will move to the different topics apart from this. That will be, I think, that is going to be the infinitesimal canonical transformation, and then we will move to the Hamilton-Jacobi principles. Okay, so thank you for now.